In this series of lecture videos for Class 9 CBSE Mathematics course, let us now begin Chapter 9 on circles. And in this chapter, the topic that is dealt with is the angle subtended by a chord and angle subtended by an arc inside the circle. Okay, so we will talk about various properties of the angles subtended by a chord or an arc, and using these properties we will solve different kinds of problems. Okay, so first of all, let's go through some definitions and understand what do we mean by the angle subtended by a chord. So for example, we have the circle and we have a chord PQ inside that circle. Okay, a chord is a line which joins 2 points on the circle, and the diameter of the circle is also a chord. It is the longest chord of the circle. Okay, the diameter is a chord which passes through the center of the circle. Any other line which joins 2 points on the circle is called a chord. So we have a chord here, PQ, and this chord PQ subtends an angle POQ on the center of the circle. So the angle POQ, which is marked as such, okay, that's the angle subtended by the chord PQ at the center of the circle. Similarly, we can have an angle subtended by this chord PQ at any point on the circle. For example, at the point R on the circle, which is on the circumference of that circle, we have an angle subtended by this PQ, which is angle PRQ. So let me mark that as well. So PRQ is this angle over here. So first we need to know these definitions. Okay, we have angle POQ, which is the angle subtended by the chord PQ at the center of the circle, and we have the angle PRQ, which is the angle subtended by the chord PQ at any point R on the circle. Okay, so we have this. Now if you notice, both these angles in this particular figure, POQ and angle PRQ, are the angles subtended by this smaller arc PQ. Okay, this is called as the minor arc, which I have highlighted in pink. So this particular angles that I have marked here, these are angles subtended by the minor arc PQ at the center as well as on the circumference of the circle. So we have POQ is the angle subtended by the chord PQ, or we can also say that POQ is the angle subtended by the minor arc PQ at the center of the circle. Similarly, we can say PRQ is the angle subtended by the chord PQ, or we can also say that PRQ is the angle subtended by the minor arc PQ at any point on the circle. Okay, now it's called minor arc because it is the smaller section of the arc compared to the other section, which is much bigger. Okay, just as we have an angle subtended by the chord and the arc at the center and at any point on the circle, we can also have the angle subtended by the major arc. So this particular arc of the circle is the bigger of the two arcs, so this is called as the major arc. And there is an angle subtended by the major arc at the center of the circle. So that angle is POQ, but because it is subtended by the major arc, that angle is over here. It's the reflex angle POQ. Okay, so that is our angle subtended by the major arc PQ, and similarly the angle subtended by the major arc on the circle is the angle PSQ, which is let me mark that as well. PSQ is this angle over here. So we need to have these definitions very clear. Okay, we can have an angle subtended by a chord, but at the same time we can also have angle subtended by the arc, and that arc could be a minor arc or a major arc. Accordingly, the direction of the angles would reverse. Okay, so when we have a minor arc, we had the angle subtended at the center as POQ, but when this angle is subtended by the major arc, then we have the reflex angle POQ. Okay, that's the basic distinction we have to realize. Okay, next we will see some more definitions and some properties of these angles. Now the angle subtended by an arc at the center is twice the angle subtended by the same arc at any other point on the remaining part of the circle. So we have this minor arc PQ. This is subtending an angle POQ at the center, and this minor arc PQ is also subtending an angle PRQ at some point R on the circle. Okay, so what this property tells us is that the angle subtended at the center is twice the angle subtended at any other point on the circle. So that means angle, this is our angle POQ. Let me mark that in a different color. So we have our angle POQ and we have our angle PRQ. What this property tells us is that the angle POQ is 2 times the angle PRQ, which is what is mentioned here. Okay, this is a property that we need to remember, and we will be using this property we will also prove this property in the form of a theorem later on, and also use this to solve different problems in this chapter. Okay, similarly, when we have the angle subtended by the major arc, the same property applies. The angle subtended at the center is twice the angle subtended at any other point on the remaining part of the circle. So when we have the angle subtended by the major arc, which again I have highlighted in pink here, the subtended angle at the center is this angle over here. So that's the reflex angle POQ. So that's POQ, but on the reflex side. So we call it as a reflex angle POQ. And that is equal to 2 times the angle subtended at any other point on the remaining part of the circle. So the any other point on the remaining part of the circle is anywhere in this part, PSQ. So we mark this point PS. So the angle PSQ is here. Okay, so the reflex angle POQ, which is subtended by the major arc, is 2 times the angle subtended by at the circumference, which is PSQ. Okay, POQ is 2 times PSQ. Now let us look at the first theorem in this chapter, and the theorem states that equal chords of a circle subtend equal angles at the center. That means if we have multiple chords inside the circle, and if the lengths of those chords are equal, then the angle subtended at the center will also be equal by each of those chords. So for example, in this figure here, we have 3 chords. The first chord is AB, is 1 chord. We have a chord CD, and we have a chord EF. Okay, what this theorem says is that if the lengths of these chords AB, CD, and EF are equal, then the angle subtended at the center by these chords will also be equal. That means angle AOB will be equal to angle COD will be equal to angle EOF. Okay, that's our first theorem in this chapter, which states that equal chords of a circle subtend equal angles at the center of the circle. Okay, so that means we will have this angle to be equal to this angle over here, to be equal to this angle over here. So all these 3 angles will be equal, given that the lengths of the chords are equal. That is, the length of AB and the length of CD and the length of EF are equal. Okay, so let's prove this. Okay, given that we have the 3 chords AB, CD, and EF are equal to each other, then we should get angle AOB, which is this angle here, angle COD, which is this angle here, and angle EOF, which is this angle here. They should be equal. To prove this, let us consider the 3 triangles which are formed here. So triangle AOB is our first triangle over here. The second triangle is a triangle COD. That's our second triangle. And the third triangle is EOF. Okay. Now in these 3 triangles, what observations can we make? The first observation is that the length OA of this triangle, okay, is equal to the length OD of this triangle, and that is equal to the length OF of this triangle. Why? OA, OD, and OF are all the radius of the circle. They are the radii of the circle. That is, these are lines joining the center of the circle to the circumference of the circle. So the radius drawn from the center to any point on the circle must have the same length, right? So OA is equal to OD is equal to OF. So these are all radii of the circle. So they are all equal. The second observation is that the length OB. OB is another radius of the circle. OC is another radius of the circle, and OE is the third radius of the circle, right? So so OB, OC, and OE, they are also equal. They are all radii of the circle. So for these three triangles, the second side OB, OC, and OE are also equal. So we have one side of the three triangles are to be equal. Then we have shown that the second side of all the three triangles are also equal. And then we are already given that the base side of these triangles, for example, the base side AB for this triangle AOB, the base side CD for this triangle COD, and the base side EF for this triangle EOF, they are also equal, and that is given in our statement. Okay, so all these sides are equal. So we have that for these three triangles AOB, COD, and EOF, all three sides are equal. OA equals OD, OB equals OC, and AB equals CD for these two. Similarly, OA equals OF, and OB equals OE, and AB equals EF. So all these three triangles, that is triangle AOB, and triangle COD, and triangle EOF, are congruent to each other. So that is achieved by the SSS congruence, that is side 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 congruence. Okay, because all the three triangles are congruent to each other, by the CPCT rule, which is the corresponding parts of congruent triangles rule, the other parts of the triangle will also be equal. So therefore the corresponding angles will be equal. The corresponding angles of these three triangles are angle AOB, angle COD, and angle EOF. So they are also equal. Okay, since we have proved that the three triangles are congruent to each other by CPCT rule, the corresponding angles are also equal. So we have proved that angle AOB is equal to angle COD, which is equal to angle EOF. So that means equal chords equal chords of a circle subtend equal angles at the center of the circle. So because we have these chords A, B, C, D, and EF to be equal, the angles they subtend at the center of the circle are also equal, and hence we have proved that. Okay, next look at the second theorem, which is nothing but the converse of this first theorem. Here in the first theorem it says equal chords of a circle subtend equal angles at the center. The converse statement would be, if the angles subtended at the center are equal, then the chords must be equal, right? So we will make that statement for the converse of theorem 9.1. We will call that as theorem 9.2, and we will also go on to prove that theorem. Okay, so theorem 9.2, which is the converse of the theorem 9.1, states that if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. So that means if the given statement is now that the angles at the center are equal, the angles subtended by the chords at the center are equal, we have to prove that the lengths of the chords are equal. So what is given now is angle AOB, which is this angle, is equal to angle EOF, which is this angle, which is equal to angle COD, which is this angle over here. So these three angles are given to be equal, and we have to prove, okay, we have to prove that the lengths of the chords are equal. We have to prove that AB is equal to CD is equal to EF. Okay, to prove that, let us again consider the three triangles that we have here. Triangle AOB, and triangle COD, and triangle EOF. And these three triangles, again, we notice that the side OA of triangle AOB is equal to the side OD of triangle COD, which is equal to the side OF of the triangle EOF. Okay, so that's one side equal because they are all radii of the circle, and the radii of the circle drawn anywhere from any point on the circle to the center must be the same. So OA equals OD equals OF. They are because they are all radii of the circle. Okay, next we know that it is given in our statement that the angles subtended at the center are equal. So AOB is given to be equal to COD, is given to be equal to angle EOF. So therefore these angles are equal, and it is given. And the third dimension of these triangles, which is the side OB is equal to the side OC, which is equal to the side OE. So the side is also equal, again, because these are all radii of the circle. So again, OB equals OC equals OE. So with these three dimensions being equal to each other, so we have one side of the triangle equal, we have one angle of the triangles to be equal, and we have a second side of the triangles to be equal. So we have a side, an angle, and another side of the three triangles equal to each other. So therefore, these three triangles, triangle AOB, triangle COD, and triangle EOF, are all congruent to each other by the side angle side congruence rule. We have a side, we have an angle, and we have a side. So side angle side congruence rule. Based on that, we have these three triangles to be congruent to each other. Once we have proved that these three triangles are congruent to each other, we can now prove that the corresponding sides of the triangles are also equal by the CPCT rule, which is the corresponding parts of congruent triangles. So by CPCT, we can it is a fact now that AB is equal to CD equals to EF, because AB, CD, and EF are corresponding parts of the three congruent triangles, right? So AB, which is the base of this triangle, and CD is the base of this triangle COD, and EF is the base of the triangle EOF. So by CPCT rule, AB equals CD equals EF. So therefore, we have proven that if the angles subtended by the chords at the center of a circle are equal, then the chords are equal. So the chord AB is equal to the chord CD, which is equal to the chord EF. So if the angles subtended by the chords are equal at the center, then the chords are also equal. Okay, hence we have proved that.